An electromagnetic tug is proposed, an orbital device consisting of solar panels, framework, parallel conductors, already in orbit by other means. One conductor is exposed to Earth's magnetic field while the other is shielded. An electrical current is run down one conductor and back through the shielded conductor. Calculate the force acting on 1 kilometer of wire, maybe kilometer, 10 amps, oriented perpendicular to the surface of the Earth. And we assume that the Earth's magnetic field is 35,000 nanoteslas, which I'm going to say is 35 microteslas. Same thing, I just like smaller numbers, easier to visualize. And oriented due north. Let the entire apparatus have a mass of 2,000 kilograms. What is the acceleration of the apparatus? Okay, so first thing we're going to do is we're going to draw a picture. So this is going to be Earth. This will be the direction of north. This will be the, I probably don't need that arrow there. Ah, no, made life more difficult. Fail. Earth. And we have our conductor, like so, a little bit straighter. There we go. This is going to be up. I'm going to say the current goes up. They don't give us a direction, up or down. Doesn't matter. Perpendicular. Okay, this is probably a good enough picture. So I'm going to go with this picture, and I'm going to say, since we have a force involving charged particles, I'm going to use the equation force equals QE plus QV cross B. And that's vector, 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 and vector. So there's no mention of an electric field, so we assume that the electric field is 0. Now we have QV cross B, where the charges in this case are going to be electrons, and they're going to be moving within the wire. So another way to visualize this equation is velocity is in meters per second. We take that per second and move it under the charge. Now we have charges per second. Charges per second is a fancy way of saying current. So another way of writing this is force equals IL, which is the length of the conductor, cross B. So same equation, just a different way of viewing it. So now I think we actually have, and then I'll, do we care about the force? No, we just care about the acceleration. I'll find the force first. So the force then is going to be the current, which is 10 amps, times the length of the wire, which is 1,000 meters, because it's a kilometer. And we're going to multiply that by the magnetic field, which is going to be 35 times 10 to the negative 6 teslas, microteslas. Yep. And so the total force we're going to have on our wire, our tug, is going to be 10 times 1,000 times 35. 35 times 10 to the negative 6. 35 times 10. Yep. And that gives us an answer of 0.35 newtons, which is not many newtons. So, yeah, that's not a lot at all. So then we use the idea that force equals mass times acceleration. Rearrange this, we get acceleration equals force divided by mass, which is 0.35 divided by 2,000. That's supposed to be a 2 because 2,000 kilograms is its mass. Divide answer by 2,000. 1, 2, 3. And we get 1.75 times 10 to the negative 4th. 1.75 times 10 to the negative 4th meters per second squared, which is pretty slow. So let the entire apparatus weigh that. What is the acceleration? So we want to find, this is going to be the magnitude. We also want to find the direction. So the direction is going to be L cross B. So this is the length of our conductor. Magnetic field is north. We're going to do right hand rule. We're going to place our hand first in the direction of the current, and we bend our fingers in the direction of the magnetic field. So up, bend it, fingers to the north, your thumb points out perpendicular. In this case, it's going to point into the page, which if we look at this as north, this would be the direction of force, which is west. So we could either go west or east, depending on which direction the current's going, with this sort of setup here. So what acceleration does it experience? So the acceleration is going to be 1.75 times 10 to the -4 meters per second squared, which is pretty slow. It's like 0.175 millimeters per second squared. And if the current goes up, it's going to be moving towards the west. If the current is going down, it would move towards the east. So you'd only be restricted to east or west because the magnetic field of the Earth is going to be to the north. So, yeah, evaluate the potential electromagnetic tug to operate in low Earth orbits. As long as you don't have to get there very fast and you only want to move east or west, seems plausible. Maybe. It could work. Hope that helped. See you next time.